Okay, we are recording now. So going back, this should just be historical context. And then first discovered, ED, by Giuseppe Peano in 1890. Now here, you need to say, it's important for your talk to say that Peano gave a set, you can say set theoretic equation for this function.
A set what?
A set theoretic equation for this function, or you could say he gave an algebraic equation. It's really not algebraic though. It's set theoretic equation for this function. And I wouldn't give that function. Sagan does, it's easy to give, but I would just say he gives a set theoretic description of this function and gives an incomplete proof that it is continuous and onto. However, it is correct, but there is no geometric intuition at all. So you need to say that Peano's paper contains no geometry at all. That's why Hilbert's interested in it. So in this next thing that you have, Hilbert dissected Peano's proof with an eye to discover that inherent geometry.
Okay.
So the movement here, mathematical history, is that first was Cantor, who showed that there is a one-to-one onto function from the unit interval to the unit square. And actually, I would say that rather than talk about cardinalities. There'll be students there that won't know the word cardinality. Okay. So I would say that there exists, Cantor showed that there exists a one-to-one and onto function from the unit interval 0, 1 to the unit square.
Okay.
And this motivated Peano to see if there was a continuous function from the unit interval to the unit square.
Okay.
Someplace in here, you need to say that this was completely unexpected and most all of mathematical research stopped immediately while this situation was understood. So these things are absolutely remarkable historically. And then it's true that Hilbert's whole purpose was to dissect Peano's proof with an eye to discover that inherent geometry. He published that geometry and simultaneously defined a simplified construction with a new proof. Now there's a quote in Sagan. I'm going to get Sagan and see if I can find this quote, but it's also in our monthly paper that would be good to use right here.
What monthly paper?
The one that just came out. That's the one you have it with Sonia and Emily and Tong and me.
Oh, okay.
So do you have Sagan's book there?
Yeah, I have it. So like what page are you referred to? Like,
Well, I don't know yet. I'm looking at it.
is it about piano or is it about Hilbert?
This is about the geometry.
Oh, okay.
This is about either this geometry that Hilbert did for his curve and the piano curve. This is on page 10 of Sagan, starting with line 6.
Line 6. Okay,
Page
I see.
10, line 6.
Yeah.
And here, that's a paraphrase. I think in this monthly article, we actually give it. I don't see it in there, but starting on line 6 of page 10, E.H. Moore was from the University of Chicago. He is considered the first American trained, or one of the first American trained mathematicians. But he described the space filling curve, the Hilbert's work, as luminous to the geometric imagination. So that actually begins on line 7. It's the end of line 7. So the situation here is that Cantor was first. It shows there's a one-to-one onto function from the unit line segment onto the unit square. And that was a showstopper for mathematics. Essentially, all of mathematics stopped while this was investigated to see how this could possibly be true. Up until then, people assumed that these were just completely different entities.
Okay.
And then Peano wanted to see if there was a continuous function from the unit interval onto the unit square, something that was also, nobody even considered it was so outrageous, but he found it. But his proof used a set theoretic function that contained no geometry. And then Hilbert's contribution was, he was interested in this, but he was very geometric and he was interested in what the geometry of this function was. And he studied it and he figured out what the geometry of the piano function is and figured out a simpler way to describe such a function. And that function is different, but it's called the Hilbert function.
Okay.
And what you're going to do in your talk is you're going to use Hilbert's geometry to investigate the piano function. And E.H. Moore was probably the US's best mathematician at the time. And he referred to Hilbert's discovery of that geometry as, and that's a good quote, luminous to the geometric imagination.
Okay.
So this leads into what you're going to do for the talk. So in the talk, you're going to use Hilbert's geometric approach to describe an arithmetic description of a full, you could say, to analyze the full arithmetic of the piano curve, or the entire arithmetic of the piano curve. And by arithmetic, I mean, given a decimal in 0, 1, where does it map? How do you find exactly where it maps? And how do you find the nature of the piano curve at various points, providing you're given their decimal representation? So this, what you have here that I'm looking at, the two issues with the piano construction were, and piano really didn't give a construction, he gave a function, a set theoretic function, or piano's proof, you could say. The two issues with piano's proof were there was no geometric construction, and the proof of continuity and space filling were incomplete.
Okay.
Now here, what you want to emphasize is that this is the Hilbert description of the geometry of the piano curve. So we're using Hilbert's method to describe the geometry of the piano curve, and that's based on 4 piano patterns.
Okay.
And each one will have a beginning vertex and an ending vertex. There's the first one, and it's called P11. And at this point, you want to say why the vector 1, 1 is used to describe it is because that describes the beginning to the end vertex.
Okay.
And this will then be P minus 1, 1. No, 1 minus 1, you are right. And then I would suggest that you click through and just do the first 2 like this. And then with the last 2, they both come up at once with their beginning and end. So
Okay.
you introduce by doing the beginning to the end, then the diagram indicating how you'd go from the beginning to the end, how you enumerate the squares. And what you want to talk about is we have 9 squares here, and we want to write them in a linear order, first, second, third, or 0th, first, second, third, and the arrows tell you how to do that. You begin at the green dot, and that square is the 0th, and then you go to the next one, which is the first, and then the second, the third, the fourth, up to the 9th. And each one of these patterns tells you how to do that, and as a notation. So maybe I will share my screen right now, because I'm looking at your stuff. So there we are there. Then this one, there's the pattern. And again, you can say you begin with the green initial square, and then this enumerates the subsquares. There's a 0th, a first, a second, up to a 9th. And now
Okay.
when I click again, it'll give that notation 1 minus 1, because from the beginning vertex to the ending vertex is in the direction of 1 minus 1.
Okay.
And now for the next click, I would have everything come on. The beginning and the end,
Okay.
the pattern, the notation. So that will save just a bit of time, and they get the idea by now. But there are just 4 piano patterns.
Okay.
So we are looking at the Hilbert geometry. And then this will begin a inductive construction. And the inductive construction is going to inductively label all of these triadic subsquares. So you are going to label, that's what the induction does. It tells you how to label all of the triadic subsquares. So here is the first stage and the initial pattern and its first numbering. So we go through 0, 1, 2. So here's what that looks good. This is what you talked about before, how to number. And now you want to, as you go through, you want to indicate that this not only numbers the subsquares, but it's going to create a relationship between the base 9 intervals, the primary base 9 intervals, and the subsquares. So I0 is going to correspond to S0, and I1 is going to correspond to S1. And I think it would be good to just say that I0 is the interval 0 to a ninth, and I1 is the interval 1/9 to 2/9, and so on.
Okay.
So there is the first inductive step. Now we're going to divide each of those squares into 9 subsquares. And then we're going to assign patterns to each of the subsquares. One at a time. Yeah, this looks good. This is exactly what the second stage is supposed to do. And at some point, maybe here, you notice that the terminal pattern of any square is the same as the initial vertex of the next square. So the terminal vertex of any of these subsquares is the same as the initial vertex of the next square.
Okay.
That you can just say in words. So now we continue this process. And now S00, S01, S02, and so on. Now you don't want to go through this whole thing. I hope we're not going to. What happened here? So I would have another slide where you can say and so on, but I might do one more square, S10, just to show how it works. And then in one more click, I would have them all labeled.
Like all of the 81 smaller square?
Yeah, it won't take too long.
Okay, it's not take too long. I'm just like, is that true?
Yeah, but I would do S10 to show how that connection goes.
Okay.
And then I would just have a slide that gives them all to indicate now that you have a relationship between all of the second level base 9 intervals and these squares.
Okay. I should replace it.
I think, yeah, oh, I see. So we have the wrong, you have two different patterns for this. So it's the 1, 1 pattern on the left, and it's the -1, -1 pattern on the right.
Yeah. So I'm just like want to show, I want to show the audience like at a level and state. We have something like this.
Yeah, but something is wrong here. Sigma 4 should be sigma 4, 1 should be inside of sigma 4. First of all, those two patterns should be the same.
Why?
On the left and the right, they need to be the same.
Oh, like it's like the X sigma 4. So 4 is here. 4 is like the middle one. So I just replace the pattern and the middle one to this pattern?
Um, Sigma 4 1 is, first of all, the basic patterns of these two need to be the same.
Why is it? Why is the pattern to be the same? Like, cause this, like, because like this is the initial pattern, so like 4 will be like -1 pattern.
Well, you have a 1 1. The
So the initial is like the level n tridexters where have 1 1 pattern. So I
Yeah.
just show that the X sigma 4 have -1 pattern.
Oh, then your right-hand square should be the sigma 4 square. It should be the exact same size as the sigma 4 square.
Oh, like
Otherwise,
you mean like the size is smaller?
yeah, the size of sigma 4, the size of sigma 4 on the right, if you can, what I would do is I would, if you start with the one on the left, that's fine. Then I would put a color in sigma 4 so it's
Okay.
obvious which is you are looking at, a light color like light orange or something.
Okay.
Then on the right-hand side, the whole right-hand square should be that size and that color.
Oh, okay.
Or maybe it can be slightly larger, but it definitely should not be the same size as the original one, or it'll be confusing. It was to me right now. And then sigma 4 1, I would do sigma 4 0 to get you started, because sigma 4 0 would be the upper right-hand corner.
Oh yeah, I think I put sigma 4 0. Am I?
You have sigma 4 1, but
Oh, why? Guess what you share me right now is the top right corner is sigma 4 0.
the top right corner of sigma 4 would be sigma
It's,
4 0.
yeah, it's what I see right now on what you share.
Oh, I actually can't see that because the, hang on. Oh, what happened there? Because the little picture's in the way. Oh man, I lost the whole thing. Oh, I see. It's actually behind. That's inconvenient. Oh, I see. Yeah, I see where you have sigma 4 0 now in there. Yeah, I would make these, this right-hand square needs to be small. That's the issue.
Okay.
I think if the right-hand square is small, it'll be fine.
Okay.
But I would also use color.
Okay.
And there you have, you're doing all of these here, but I would not do all of them. I would,
Just 2 of them and then pop up the whole thing.
yeah, that's what I would do, because otherwise it'll take you too long.
Okay.
Now, number 3 here, I would not call this, you're sort of done with the inductive construction at this point.
Okay.
This is, you could call it the decimal arithmetic of the piano code. the decimal arithmetic of the piano curve.
Okay.
And here, suppose x is 0.027 dot 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 base 9. You need some more words. Then
Okay.
x equals this, and f sub p of x equals this.
Okay.
Now, in the next part, in general, if x is point A0, A1 dot dot dot, where a the ends are these, then x is equal to, this should be I and then sub a sub 1. So this is a double subscript. I sub a sub 1 intersect ai sub a sub 1 a sub 2 intersect.
I don't know if like PowerPoint let me to do it because I tried yesterday. I cannot do like the 2 subscript.
In LaTeX?
No, this is not latex. This is PowerPoint.
Oh, in
Like,
PowerPoint.
yeah, like the subscript, but like 2 times subscript. I was trying yesterday, but it's not working at all. That's why I just put A and like I just reduce the size of number 1 to make it smaller than A.
Yeah, but it doesn't. In this case, I would just eliminate the in general part. You could do it in LaTeX and then copy and paste just a little PDF and put it in there if you wanted to.
Okay, I would do it in latex and then just take a screenshot and put it here.
You can just, once you get the PDF, you can just copy from the PDF into this. You can copy just a piece of the PDF and paste it in.
Okay, I can try now. I think you sent me that stuff last week.
Yep. Let's see here. Now, on the right-hand side of this picture, you have I0, and then you have I0. So it's a little confusing here because you don't picture I0 or S0. S0 is the big one, so I would put I0 in a color as well, not just white. So I0 and S0, S0 you could make bigger in this picture, but I0 should maybe be a color also, like green or red or something.
Okay, so like you want me to put like some color in like the whole I0, like the whole length?
I0, it's just like you have two colors, yellow and blue on top, and the next one should be, I mean, it should rather be a first color like green, and then yellow on top of that, and blue on top of that. And then at the end, you could put one little dot for the 7, where that is. If the S0 was bigger, you could actually see it.
Okay. I'm trying to do it right now.
No, don't do it right now. Let's go ahead here.
Okay,
We'll run out of time. The achievement is not a good word here.
Yeah, I'm trying to find another word. I don't know what word should I use.
Didn't I made all these corrections. Maybe I didn't send them.
Oh, you send them, but like I don't think like you send me something, but like not changing the achievement stuff, I believe.
Well, I will look when we're done because I edited this whole thing and put those in there. Well, let me look right now. Hang on for a second. Oh.
Okay, let's see, what's the word? Oh, yeah, I saw it. You say our result.
There you go.
You say our result, not
Yeah,
achievement, just the result.
yeah, our results.
That's a better word. Okay.
Now here, what does 1, 1 mean?
Which one? Oh, it's 1 3 over. Oh my God. It's 1 3. It's not 1 1. It's 1 3 1 3. It's 1/3 1/3. I mean.
So you,
Uh,
so that as far as I see,
maybe 1/3 1/3.
uh, that arrow and the 1, 1 should just be removed.
Uh, okay, so like the arrow and the 1 1, you just want the whole thing just being removed.
I think so. Let's
Uh,
eliminate that and let's take a look.
okay, sure.
So I am screen sharing with you again, it looks like. Am I?
Yeah.
Or
Yeah, I'm used to sharing screen right now.
you are sharing or I am?
You are sharing right now.
Yeah, I'm going to stop and let you share so I can see this page.
Okay. If I delete the whole thing, I need to edit the animation again. Just okay. Let me take a look. Oh, yeah, this works.
Okay, share it with me. Let me take a look.
Okay. Presentation. Can you see it?
Yeah, I can see something. Okay, so 1/3, 1/3 equals. And what are you going to say from there?
I'm gonna say like let's take a look at point 1/3 1/3. Since this is in like it's the part of 4 different Strilix software. One is S0, S0A, and then like I will keep moving on from it. I will just explain like the first line, and then I will say like the same thing happened for the 3 different case, or the
But
3 other case.
But is this a 1-to-1 point, a 2-to-1 point, a 4-to-1?
Oh, at the end I say that the 0.088 in base 9 is the same as the 0.100 in base 9. And the same
Yes,
thing.
yeah, and so I would do these, let's go back and do the first one. Let me see you click through these last four. There, that's good. Okay, so there's the first one. And you could say, now you need to explain this, that the point 1/3, which is that blue dot, is in the S08 square, and it is the terminal corner of that, the exiting corner. And so it is f sub p of 0.08888 because it's equal to S0 intersect S08 intersect ... Now do the next one and say it's also in, I would just do one more here. And
okay.
you could say it's also in the S10 square.
Okay, I would the animation of 1314. Okay. I don't know, it's where. No, it's not where.
That's okay, but let's just talk about it and then you can put it in there. But I would do the second one and say then since it's in the S10 square, it's equal to S1 intersect S10 intersect S100 because it's always that's the initial point of that square. So it's also equal to f sub p of 0.1000, etc. But now I would say that those two domain points are the same, just different notation for the same point.
Okay.
So this is not, for sure, this is not a 4-to-1 point because those two are equal. And then say the same thing happens with between S48 and S50.
Okay.
So this is actually a 2-to-1 point.
Okay.
Okay, let's see where we are after that. So yeah, so we'll prove there are no 3-to-1 points. Yeah, I would, I see. We use the base 9 representation to show that determine if a point is 1-to-1, 2-to-1, or 4-to-1, and we prove there are no 3-to-1 points. Before you say number 3,
Okay.
I would say that the 4-to-1 points are dense, and
Dense.
there are only countably many of them.
So like countably many of 4-to-1 point.
Yep.
Is it true? I think it's true.
Yeah, it's just there are only countably many lines, and the lines intersect then in only countably many points. And that's the only possibilities for the 4-to-1 points, where two triadic lines intersect.
Okay, sure. I think this only happen when the two triadic lie in the different level, not at the same level.
No, but the only possibilities are when two triadic lines intersect. That's the only possible way you could get a 4-to-1 point. And there are only countably many such intersections.
Oh, okay.
But 4-to-1 points are dense. And you could say that the 2-to-1 points, there are as many of those as there are real numbers. But every 2-to-1 point lies on a triadic line. And then finally, you could say most points are 1-to-1 points. And if they ask you, what do you mean by most? You could say topologically, or you could say it's a residual set.
I don't think we have Q&A section after the presentation, like. So I
You
don't
might.
think.
I think you might.
Oh, okay. It's gonna be a long night.
Yeah. Let's go a little farther. Now, I would leave that. I would have number 3 to be there are a countable dense set of 4 to 1 points. Every 2 to 1 point lies on a triadic line.
Okay.
And you could put in quotes, most points are 1 to 1 points.
Okay.
And that would be the end of this slide.
Oh, okay.
What's
So
next here?
I don't think like there is any next slide. That is the end of the presentation too. When we
Okay.
show like our result.
So I think that you need a couple more things. I would maybe have another slide to say that we also show that the replacement table is generated by the action of the Klein 4 group. And you could say at the end of that, you could say on the vectors which label the patterns.
Okay.
The action
So
of the Klein 4 group on the vectors that label the patterns.
like, do we need to show like what is our apply forward?
What, pardon?
Like, do we need to show like our apply forward, like our addition of the apply forward, like?
No, I don't think you have time to talk about this. But you can leave it as something that we can show, but you don't have to show it. Just say
Oh,
that
okay.
this is what we can show.
Oh, okay.
But you also you definitely need a references section.
Oh, okay. The references.
Yeah, so there should be a bibliography on this paper, and you should include those two books or manuscripts that you sent me the PDFs of.
Okay. So like, should I just copy the whole thing from like your reference on the draft that you sent me?
We want all of the references in a bibliography list. If you look at that monthly paper that I sent you,
Okay.
look at that right now, maybe share that with me.
I think you share me the draft that you have written for our paper, and it has like a
Oh,
whole
yeah. It's in our paper, right? That bibliography, I started it.
Okay, let me share. This will be research. Okay, I think at the end we have like
Yeah, there it is. Yeah, you want to show this and add those two papers, two books that you sent me the PDFs of.
Okay.
Those should be in there, and have a look in those for the one has applications to.
Oh, I have read through like the two book already.
You did look through them?
Yeah. There's only like the section talking about the optimization algorithm using the piano curve when they use the octa tree and like the penta tree. I believe like that is the section that I understand because I'm studying it in my computer science class right now.
Uh-huh.
And like
So if somebody asks you for applications of this or how can this be applied, you should be
I,
prepared to at least say that.
okay, I like, yeah, I look at the optimization book and I understand most of the wording inside. So yeah, I definitely can say something about application.
Yeah. Okay. Uh, Kang, I would like to meet sometime this week, maybe on campus, when we go over this. Can we meet on Wednesday afternoon by some chance?
Like what time in like during afternoon? Like what time?
Yeah, I have meetings on campus at until 3 o'clock.
Okay, until 3. Let me take my schedule. I don't know if I scheduled some meeting already. Okay, Wednesday. Uh, I will. Oh yeah, I will have meeting until 3 too, so I can definitely meet after 3.
So let's try at 3:30,
Okay.
and I will try to find us a room, just reserve us a room.
Okay. 3:30. Like, can you send the information when you reserve a room already?
Yeah, of course, I will.
Okay.
And so what I'm going to ask you then is to go over your entire talk. So I would like you to present the entire talk. Kang, the entire talk, you know.
It's a little bit scary. Right now.
Well,
Oh,
of course.
for the reference, like, should I just okay? Here's this our reference, and like just leave it there. Like, should I say something
Yeah,
else about it?
no, you don't have to say anything about the references, but you should, it is usual to put up your list of references at the end.
Okay. Oh,
In
it's like
other disciplines, you would say, you would give individual references as you speak and in detail. But in math, it is typical to just tell the story, tell the mathematical story, but then at the end have a list of the references.
okay. So this would be like 13 reference, I believe.
Yeah,
It's
there
around.
are several. There are, you could use the list that I put in the paper and then those two more, add those in. And you can use the same format to put them in.
Okay. Uh, yeah, I think that's all my question for the presentation.
But it's
On
not all mine. I'll ask more on Wednesday, so we will see.
okay. Uh, Another question, cause is on what registration time. So, like, do you plan to do any same research next year?
Will I do any research next year?
Yes.
Um, I don't know if I'll be able to yet. So don't plan on it, but I will let you know, and I will know before April is over. But I won't know immediately because I have to have a meeting with the dean about it.
Okay. Like, okay. So, cause I don't know, I'm planning to do some more research because I'm changing my plan. I want to earn PhD in math now rather than computer science.
That's good, and actually you can we can find a program where maybe you can sample some of each before you actually decide. But yeah, that would be fun.
Cause I got rejected for like Curry for on three, even like the math research.
Oh, did you get the curry?
No, I got rejected.
Oh, you got rejected?
Yeah, by the math research, with the math research.
Oh, it's too bad. I know there aren't enough math people who are doing it. So there are only a very few number of slots that they allow.
Oh, okay. Also, I apply for like the DUR next fall with Professor Tina.
Mhm.
And I write down your name for the references, like
Yeah.
for the on and also for the Professor Adam Wu for the independent research next fall too. So I apply for 2 more research next fall in math department.
Okay,
And
but if you get those two, then that's one more would be too many with me. So, but I hope you take the DOR if you can get it. That should be very good.
oh, and like I put your name down as the reference.
Perfect.
Like, okay, so like, and the prof say that they got my gonna ask you something about me too.
Yeah, they usually do. Usually we do it in a group meeting, but now since we're not together, probably they will just write an email. But but I will
Okay, because
definitely give you a good reference.
yeah, because I scheduled my whole plan for like until my senior year, and I still want to do some more research with you. So anyway, this thing is fun.
Yeah,
Like,
you have done well, and but you should have experience with someone else too. But right now, let's work on this talk. So
yeah, so like I guess I don't know. Like next, like I'm technically need only one more class for math major because I'm almost done with math major. So like the rest page is just for research opportunity. So I'm gonna
research
try.
opportunities, but also you should take advantage of more upper level classes if you can,
Okay. Like
because that will help you in graduate school a great deal.
do you have any reference? Like
Uh,
if I'm thinking about like applied math or like interdisciplinary like section between like math and computer science, like do you have any?
yeah, so there are several that could be good. Have you taken differential equations?
Oh, I took it like in my first year already.
Then maybe PDEs, partial differential equations.
Like the second differential equation, right? Like
Second differential equations, yeah, that is good. And you've taken abstract algebra, yes?
yeah, I took it already.
Yeah, so there are second courses in both abstract algebra and real analysis, Math 352 and Math 344.
Okay,
You should take one of at least one of those, maybe both.
okay,
And those when I teach Math 344, it's more like a graduate level course.
okay,
Not everybody teaches it at that level, but I do. Um,
okay.
so that will give you a very good help for graduate school.
Like, are you planning to take like to teach any course next year too?
No, probably not. Probably not. All
Okay.
good things come to an end eventually, Kang.
Like, cause my brother will come here next year, and he want like when I tell him about you, he want to take course from you too. So,
We can meet over a tea. Kang, I have to go. I
okay,
will write you an email about Wednesday.
okay. Thank you.
Yeah,
Have
see
a
you
good
soon.
night. Yeah,
Yeah,
see
you
you.
too.